In the previous video, we designed the stop and wait protocol. No manager worth his penny will hire us based on the previous design. Imagine the company spending a fortune on a GPPS link and you deliver this protocol that gives a pittance of the overall bandwidth. So you're wondering, what is this quote doing here? Experience is a very powerful thing. So Mark Twain says, a man who carries a cat by the tail learns something he can learn in no other way. So basically, by going through the previous design, we have gained a lot of experience. So we now have a powerful set of functionality based on which we can design better protocols. And that's what we are going to do next. So this is just a rehash of what I have said, but in plain words. So in this video, we are going to look at a class of protocols called sliding window protocols that can significantly improve performance compared to stop and wait protocol. So this is the general idea behind sliding window protocols. So pay close attention. So in stop and wait protocol, we send a packet, then we stop and wait for the acknowledgement to come back, and then we send the next packet. By the way, in this figure, packet, I'm showing it as the size. ACK, its size is so small that the transmission time is negligible. I'm just going to represent it by this single line. So the main problem with stop and wait protocol is that during this waiting time, you are not utilizing the link. Thereby, you are wasting the capacity or bandwidth of the particular link. The sliding window protocols overcome this problem by keeping the link busy even before you got the acknowledgement. The acknowledgement, as you can see, didn't come until this point, but you didn't stop. You are continuing to send packets. In this particular example, I have sent a total of 5 packets here, thereby my utilization has increased 5 times. So this was 3.8%. Going with the numbers I used in the previous video, in this case it became 19%. So how many packets to send? Here the number 5, this is called the window of the sliding window protocol. So you maintain a window which specifies how many packets you can send. So if I set this window equal to 5, my utilization became 5 times. Does it mean that if I set it to 1000, my utilization will become 1000? In other words, what should your window size be such that you make the best use of the link bandwidth? So there is this term called bandwidth delay product that captures this. So in this case, in sliding window protocols, a sender can send a maximum of W packets without waiting for an acknowledgement, and we are answering the question, what can this window size be? Suppose if I were to set the window size to be infinite, does it mean I'm going to get infinite bandwidth? No, because the link has a certain bandwidth. If you dump more packets than it can handle, all that happen is the packets get buffered or queued up and they will take their own time to get out. So to keep utilization maximum, basically you have to set the window size equal to this. Why? Because of the following reason. You're sending a packet, you're going to get the ACK back after some time. During this time, you want to keep the link busy. And how many bits can you send during this time? That is nothing but the data rate into the round trip time. Once you got an acknowledgement which is saying some previous packet has been removed, then you are at a state of equilibrium. You can now put an additional packet. So if you have these many bits in what is termed as the pipe, which is the link, as each packets get removed, which is indicated by an acknowledgement, you are putting an additional packet into the pipe. So this maintains an equilibrium. So we want the window size equal to roughly the bandwidth into RTT bits. By the way, this is a rule of thumb. You can definitely have it lesser than this, definitely not more than this, because then you are going to exceed the capacity of the link. Now these many bits, if you want to know the packets, you divide this by the packet size to get the number of packets. Of course, I'm assuming the packet size is fixed here. So we have seen the window aspect of sliding window protocols. What is the sliding? So at any given time, we are saying that there will be no more than W packets out in the network, that is, they are outstanding, the sender doesn't know their status. By the way, out of this W packets, some packets would have reached the receiver already. In other words, they're received, but the sender doesn't know it yet. So as far as the sender is concerned, there are W packets outstanding. It doesn't know their status. Now, as the status of these packets gets known at the sender by receiving ACKs from the receiver, what happens is you start sliding the window of sequence number to encompass newer sequence numbers. That is where the sliding is coming. So this will permit the sender to send subsequent packets. If you didn't understand, don't worry, a figure is worth many words. So here are the details of the sender side of the sliding window protocol. So each frame is going to be assigned a sequence number. For now, let's assume that you have infinite sequence numbers to assign. So each frame we are going to assign a sequence number. Now the sender is going to maintain these three variables. One is the send window size. This is what we were talking about earlier. Provides an upper bound on the number of outstanding frames. LAR stands for sequence number of last acknowledgement received. So this LAR, as you can see here in the figure, it is showing that all these packets have already been acknowledged, and LAR captures the sequence number of last such acknowledgement received. Now as ACKs keep coming, you start moving this LAR. Now LFS stands for sequence number of last frame sent. So I have sent this frame. This is the sequence number of the last frame sent. And what sliding window protocols specify is that this difference between LFS and LAS should always be less than or equal to SWS, which is your window size. So until this point, you have already acknowledged the packet. The receiver has already acknowledged the packet. So these are all fine. So this is the packets that you can potentially send all the way from here to here. But out of these packets, this is the window size. Out of these packets, you have only sent until here. You didn't send these packets. You could send these packets, but you didn't send these packets. Why would such a situation arise? So this could arise when the higher layer did not give you any packets. In other words, you can potentially send, but there are no packets to send. That is what is happening here. Now these packets, even though they are in the buffer, if possible, you cannot send because your window size is limited to SWS. Now how does sliding happen? Suppose previously you received an acknowledgement for this frame 3. Now suppose an acknowledgement for frame 4 came. Now this is going to move here. So now you put LAR is equal to this, and now you are going to slide the window. In other words, your window will begin here and is going to end here. So you have slided it. Now as a result of this slide, if you can potentially send another packet, you are going to send that particular packet. If the sender can maintain a window, why not the receiver? So the receiver also wants to maintain a window here. So the receiver window size is called RWS. This provides an upper bound on the number of out of order frames that the receiver is willing to accept. Again, a bit of terminology. Let's start here. LFR denotes the sequence number of last frame received. So it has received this last frame in order. After this, it could receive out of order packets because some packets may have gotten lost. So it could receive some other out of order packets. And LAF refers to the last acceptable frame. In other words, it is ready to accept any frame that is within this RWS window. In other words, all frames until LFR were received in order. So the receiver could potentially pass these frames up to the higher layers because they are all in order. Now these things are not in order. In other words, either it is expecting this frame or you received some frames but they are out of order, thereby it is buffering it. So as you can see, this protocol can also provide in order delivery of frames. And how many of this out of order buffered packets it will accept? Only until this point. In other words, if it received any packets outside this range, these sequence numbers, it is not going to accept. So here I have just numbered the frames. So this receiver has received frames in order until third frame. It is expecting frame 4, but it did not come. Maybe it got lost. After that, it got the frames 5. Again, 6 it didn't get because maybe it was lost. And then it got 7, 8, 9. So 5, 7, 8, 9 it accepted because they fall within the RWS window. If 10, 11, 12, 13, 14, 15 were also to come, it will accept. But if 16 frame were to come, it will not accept because it's not part of the receiver window. Even here there is sliding happening, as for example, if this hole got filled up where 4 got retransmitted and you get this, then it will slide this LFR all the way till 5. And when if 6 got filled up, it will slide all the way till 9. Now, given this background, tell me, does it make sense for RWS to be greater than SWS? No, right? Because the sender will never send frames at any given time more than SWS. So there is really no point in providing a buffer space for more than SWS packets. So RWS should be less than or equal to SWS. Now, what does it mean to have RWS is equal to 1? So in this case, when it has a buffer of only one packet at the receiver is going to accept only in order packets. That is what RWS is equal to 1 means. By the way, I'm using the word packets and frames interchangeably. So compared to stop and wait protocol, how have things changed? Now we need a whole range of sequence number. In stop and wait, we just used 2 sequence numbers. That is not going to suffice anymore. How much we will see shortly, but we need a much bigger range. Not only that, in stop and wait, the sender, if it just buffered the previous packet or whatever packet it has currently sent, things are fine. But here the sender has to buffer more than one frame because whatever it has transmitted, until it knows about their status, it may have to retransmit the packet. In other words, stop and wait is nothing with a window size of 1. Here we have a much larger window, thereby we have to buffer more packets. And similarly, based on the design, the receiver may also have to buffer. By the way, this RWS, as I said, can take on any value less than or equal to SWS. Ideally, if it is equal to SWS, that is what gives maximum efficiency. But for simplicity reasons or buffer capacity reasons, it is possible for RWS to be less than SWS. And there are a whole range of protocols based on the sliding window concept that I have covered. Go back and selective repeat. The TCP protocol itself that we will cover in detail later is based on sliding window. Now, how do these protocols differ? Basically, the actions they take on events like when you receive a frame or ACK or duplicate ACK on timeout, all these actions are going to be different for these different protocols. So what I have covered so far is a very high level overview, but how does the protocol work in practice? So there is some action you need to take at the sender as well as receiver. So what are the types of actions? Let's see. So at the action at the sender, it has to decide many things. So on receiving a packet from the higher layer, should I send this packet or should I buffer it or should I discard it? If it were to receive an ACK, should I send a packet in response to this ACK? If I were to send a packet, which packet should I send? And on timeout, should I retransmit the packet? And how should I update my timeout values? So these are all the action that happens at the sender. And as a protocol designer, you have to answer these questions. Similarly, at the receiver, there are a bunch of questions. When I get a packet, should I accept this packet or should I discard this packet? If I accept this packet or not, should I generate an ACK? If I generate an ACK, what should I acknowledge in it? So let's answer these questions. So let me start out with the receiver side first. So whenever a frame or a packet with sequence number arrives, this is what the receiver does. It compares the sequence number with the last frame received. And if the sequence number is less than or equal to this, that means it has already seen the sequence number before. Or if it is greater than last acceptable frame, which in this case means that it is outside its buffer capacity, it is going to discard the frame. Now, any frame that falls in between, it is going to accept. Now, in this particular case where it has already seen this particular frame, it is going to discard. But in this case, does it make sense to send an ACK? So no matter what, it is always good to send an ACK because you are providing more feedback to the sender. As long as the sender design is handled carefully, more information doesn't hurt. And this can definitely improve performance by early detection of losses. For example, in this case, when you are sending feedback in the form of ACKs and there are holes, you can convey information about the holes. Thereby, the sender can act on that information. Of course, there are exceptions to this. For example, in some protocols like go back N, even whenever you discard frames, you decide not to send an ACK because it serves no purpose. Now, if you decide to send an ACK, and as I said, it is always good to send an ACK, what should the ACK contain? Now, there are two types of ACK, cumulative ACKs and selective ACKs. Cumulative ACKs are simple, but they have certain performance issues. Selective ACKs are slightly more complex. At both the receiver and the sender side, it tends to increase the complexity, but they improve the performance. So let's see what I mean by these ACKs. So in cumulative ACKs, the sequence number to ACK is always going to be the largest sequence number received, such that all frames with sequence number less than this have also been received. This LFR is the one that is set to the cumulative acknowledgement. An example helps. So for example, you are receiving frames in this particular order at the receiver. And let's say the state of the receiver is such that it already acknowledged frame 3. And let's also assume that RWS is equal to 4. So if you look at it, it acknowledged frame 3. So here is how it looks. So LFR is 3, your window size is 4, receive window size. There, the sequence number that you are going to accept is until 7. So when frame 5 arrives, it is falling within the window, so thereby you buffer it. But the acknowledgement that you are going to send in response to this is still acknowledgement 3 because this is cumulative acknowledgement. You just send until which frame have you received in order, and that is until only 3. Now, since we didn't move LFR, LAF is also going to be the same. So now if frame 7 were to arrive, what would you ACK? What will your LFR be and what will your LAF be? That's right, you buffer frame 7 also because it is within the window, and you still send ACK 3 because there is still a hole in frame 4, and thereby LFR stays the same, LAF also stays the same. Now suppose the sender were to retransmit frame 4 on a timeout and frame 4 arrives after this. So now we have frame 4 coming. Now what will your ACK be? What will your LFR be? And what will your LAF be? So that's right, when frame 4 arrives, it's filling up this hole, so you are definitely going to accept it. And then you move your LFR all the way to frame 5 because until that point you have received in sequence, you still haven't gotten frame 6. So you're going to pause here, so your LFR becomes 5, and now that your LFR has changed, you have to add RWS to it, which is 4, thereby LAF has become 9. And the acknowledgement that you're going to send in response to this is the value of your LFR. Thereby, you're going to ACK until 5. In other words, I received cumulatively all sequence numbers until 5. Now, when frame 6 arrives, it's going to fill up the hole. So you're going to acknowledge all frames until frame 7. Thereby, your LFR becomes 7 and your LAF becomes 11. So this is how cumulative acknowledgements work at the receiver. So in selective acknowledgements, even when you receive this out of order packets, you do send your cumulative acknowledgement, but in addition to that, you also send a selective acknowledgement that specifies the sequence number of whatever packets were accepted. Again, an example helps. So we are working with the previous example, 0, 1, 2, 3, 5, 7. This is the order in which you received the packets. Now, when frame 5 arrives, you're going to acknowledge, this is the cumulative acknowledgement 3, but you're also saying I've received frame 5 as part of my window. Now, when frame 7 arrives, again the cumulative acknowledgement is 3, but you are now saying I have within my window frames 7 and 5, which is part of the selective acknowledgement. Now when frame 4 arrives, you are going to cumulatively acknowledgement 5 and you say, I still have 7 in my window. And when 6 arrives, you just acknowledge 7. You have no holes anymore. So here are the sender side details. So on the sender side, whenever it receives a packet from the higher layer, it has to first sequence number it. So it will just pick the next sequence number to use and is going to give it a sequence number. Now if this sequence number that it has been assigned falls within the SWS, in other words, this minus LAR is less than or equal to this, that means it's falling within the sending window, it can send the packet. Else it can buffer the packet or even inform the application so that the application will resend the packet later, in which case it doesn't have to buffer. But for now, let's assume that it is going to buffer the packet. So this is where things get very tricky from the sender side. So on receiving an ACK, whatever action you're going to do is a function of the type of ACK, and things can get very complex. For example, later when we cover TCP, you will see the lot of variants that have different actions for the same acts that come. So one thing that is common in many of these protocols is that they rely on the type of ACK, either duplicate or a selective ACK, to make some sense of packet loss, whether a packet was lost or not, and they try to trigger a retransmission. Timeout is only used as a backup mechanism. So basically timeouts tend to empty the pipe, because until you're waiting for a timeout, you're not going to send any packets, and if you're not sending the packets, you're not going to utilize the capacity of the bandwidth of the link. So you should rely on timeouts only rarely. So until I cover the TCP variants, for now we will go with a very simple version. In other words, whether you receive dupacks or selective ACKs, you use the cumulative ACK field only to advance the window. The way this works is if the sequence number in ACK is greater than LAR, you're going to set the LAR equal to the sequence number in the ACK. Remember, LAR stands for last acknowledgement received. So you're going to move the left side of the window based on the cumulative ACK. Now, as a result of this movement, your right side will also move, and as a result of this, if there is a sequence number of buffered packets that is less than or equal to this, then you are free to send them. In other words, there is space made up because some previously unacknowledged frames have been acknowledged now, and you can send some packets in place of those already acknowledged packets. I know that until you see an example, these things won't gel in your mind. We are going to see a whole lot of examples shortly. But before that, how many sequence numbers do we need as part of the sliding window protocol? See, remember that for stop and wait, 2 sequence numbers sufficed. In that case, the window size was 1. In other words, there we used 1 additional sequence number than the window size. Let's apply the same logic here. So if your window size is equal to 3, suppose I were to use 4 sequence numbers. In other words, I am going to use 0, 1, 2, 3, which corresponds to 4. Now, will this suffice? Now, this is going to be a function of the receive window size. Let's assume that RWS is equal to 1. So I will prove that for RWS is equal to 1, this number indeed suffices. So here I've just numbered the packets P0, P1, P2, P3, P4, and if you're reusing the sequence number space, P4 has the same sequence number as P0. Now suppose the receiver is expecting P4. To show that sequence number space of 4 suffices, when it is expecting 4, P0 should not arrive. Then with this sequence number space, I am done. So if the receiver is expecting 4, naturally P3 until P3 it is successfully received. So let's look at the perspective of the sender, and here I claim that the worst case scenario will happen if P3 happens to be the last frame sent. If P3 wasn't the last frame sent, you would have moved away from P0, and thereby there is less chance of confusing the P0 with P4. In this case, if LFS was indeed equal to P3, then there's a potential for P0 to be confused with P4. So in this case, This, given the fact that SWS is equal to 3, that means the sending window has to be something like this. So it has already received an acknowledgement for P0. So this has been last acknowledgement received. Since it already received an acknowledgement for 0, it would not send P0. Thereby, there is no confusion of P4 with P0. But suppose RWS is not equal to 1. In this case, I am setting RWS, SWS is equal to 3. In which case, will this be sufficient? I'll prove that this won't be sufficient. So I'm going to give you an example. Suppose the sender sent 0, 1, 2. So this is what the sender sent. And the receiver received these. So the receiver is expecting 3, 0 and 1. So it kind of progressed forward. But let's assume that all the ACKs the receiver sent got lost. So the sender is going to retransmit 0, 1 and 2. Now the receiver is expecting the next instance of 0. But now what it got was a previous instance of 0, and this is not okay. So this definitely is not sufficient. So given this, given RWS and SWS, what is the general rule of how many sequence numbers do you need? This is something for you to work out. I will provide an answer as part of the quiz. So here are some examples at last. So in this, I'm considering a very simple sliding window example, where I'm going to make use of cumulative acknowledgements at the receiver. I'm going to set a timeout value which is equal to twice the round trip time. And at the sender, the retransmission is mainly due to timeout. In other words, it's going to ignore the duplicate ACKs. So this is the assumptions I'm making as part of the sliding window protocol. And now let's see what happens. So here I have sent, because my window size is 4, I am permitted to send 4 packets. So I have sent P0, P1, P2, P3. P1 is lost. So in response to A0, because I got this packet, and remember there can be 4 outstanding packets. I don't know the status of P1, nor of P2, nor of P3, but I know the status of P0. Since it has been removed, I am permitted to send one more. Thereby I have sent P4. Now then I've got another acknowledgement for A0. This is a cumulative acknowledgement generated in response to P2. But now, since my retransmission is due to a timeout, I'm just going to ignore these duplicate acknowledgements. So I've got an acknowledgement in response to P2, I've got in response to P3, I've got in response to P4. After some time, I'm going to time out, which is twice the round trip time, and then I'm going to retransmit P1. In response to P1, since it filled up this hole and it received all these packets, which by the way get buffered because your RWS is equal to 4, I'm going to get a cumulative acknowledgement that is going to acknowledge all these packets until A4. Now in response to this, so if you can see here, I've received everything until P4. So my window slided, and now I am able to send P5, P6, P7, P8. So this is the sliding window in action. Here it's the same example as before, but now the retransmission can be due to a duplicate acknowledgement. So this all kind of stays the same. But here, as soon as I got a duplicate acknowledgement, I'm going to retransmit P1. I didn't wait for a timeout, but I'm going to ignore these other duplicate acknowledgements because I already acted on the first duplicate acknowledgement. Once this acknowledgement from after receiving P1, once I get an acknowledgement for all the packets, then I'm going to send the remaining packets. As you saw, recovery in this case was much faster than with timeout. So this is more efficient. Go back in is another sliding window protocol that makes state maintenance easy. So it's a simple protocol. So this is what it does. whenever the sender times out, the sender resends not only the packet for which it timed out, but for every other packet that it previously sent but it didn't receive an acknowledgement. Not only that, it maintains an RWS of 1, which means that the receiver accepts only in order packet and generates a cumulative acknowledgement in response to this. If any out of order packets comes, it is just going to discard those packets. No ACKs are generated. This is fine because, as I said, on timeout the sender is anyway going to retransmit all the packets, thereby RWS is equal to 1 is sufficient in this protocol. So naturally it is being inefficient because even though the packets reached successfully at the receiver, but they were out of order, you are just discarding them. But at the same time, the reason why this is used is it makes the receiver design very simple. It hardly maintains any state. It gets the next in sequence packet, it accepts. Otherwise, it's not going to accept it. So this is a simplistic protocol. So here is go back n in action. So again, the same case, P0, P1, P2, P3, this got lost. So remember, it generated an acknowledgement for P0 because it was received in order, and this is the cumulative acknowledgement. It received P2, P3, but these are out of order, so it just discarded them. It did absolutely nothing. Now the timeout is going to recover the loss of packet 1, but when it is transmitting on timeout, it's not just transmitting packet 1, it's transmitting packet 1, packet 2, packet 3, packet 4 as well. So this is the go back n. It went back and transmitted all the n packets that were outstanding. Now once the ACK for A1 comes, then it is kind of going to proceed further by transferring packet 5, so on and so forth. So here is selective repeat in action. If I were to use the same example as before where only P1 is lost, selective repeat essentially boils down to the example sliding window protocol. But to show the effectiveness of selective repeat, I'm going to vary a few parameters. Basically, I've set the window size now to be equal to 5 and I've considered multiple losses. Basically, P1 as well as P3 are both lost. Since the window size is 5, this is the usual sender sending 5 packets. In response to the first packet, A0 got sent, so you sent P5. But since P1 was lost, the acknowledgement that you sent is as follows. So this is the cumulative acknowledgement and this is the selective acknowledgement that you have sent. Now in response to this ACK here, the sender has figured out that there is a hole in P1. In other words, P1 didn't reach, thereby it retransmitted P1. And again, in response to this ACK here, again the sender figured out that P3 was lost and thereby it retransmitted P3. Now when P5 came, as I said, because you sent the selective acknowledgement, so the ACKs take these form in response to P5, P1 and P3. I'll let you figure this out. So when this ACK reaches the sender here, there are already 5 outstanding packets, P1, 2, 3, 4, 5, thereby the sender cannot send any more packets. Now when this pack comes, this point I am kind of representing again here, so it's the same thing, A2, P5, P4, so A2, P5, P4 has come. The sender is now able to send 2 more packets because you acknowledged P1, P2 as part of this. Thereby it was able to send P6, P7. And similarly, when this ACK represented here comes, it has acknowledged until A5 and you have A6, A7 already out there, thereby you are permitted to send 3 more to make the count 5, thereby you send P8, P9, P10. So as you can see, selective repeat is lot efficient because it could quickly figure out the holes and retransmit those packets, and not only that, as the window size moves, it's able to send new packets. Flow control is another feature which reliable data transfer protocols can provide. I will cover it in lot more detail when I cover TCP. Here I'm just going to tell it in passing. So basically, flow control provides a means for the sender to prevent overflowing the receiving buffer. So receiver buffers, depending on the capability of the receivers, they can be small. In other words, sometimes the sender may be very powerful, whereas the receiver may be a dumb terminal, in which case you don't want the sender to overflow the receiver buffer. The way the flow control can be handled as part of reliable data transfer is by the receiver informing the sender how many frames it has room to receive. And sender is always going to respect this. For example, even if its SWS is very large, it will not send packets even though it has packets to send, because the receiver told it that it does not have space to accept these packets. So we will see more of this when I cover TCP. So here is a summary of what we learned in this video. Basically, that stop and wait doesn't perform well. So we relied on windows of packets to improve performance. This is the sliding window protocols. These are definitely more complex. You have to handle a range of sequence numbers. There are different types of ACKs, as well as the actions at sender and receiver in response to events can also be quite complex. In addition to reliability, these protocols can also provide in-order delivery as well as flow control. So we have reached a big milestone here. We can congratulate ourselves. So what we have achieved so far is between two nodes, A, let's say A, B, we can now reliably transfer data from A to B. Network layer as such doesn't make sense here because there are only two nodes, and transport multiplexing, it's a very small functionality, it can be handled. As you can see, we now have a building block where we can transfer data between two nodes A and B. In future, we will use this building block to make many nodes communicate with each other.